Hello everyone, welcome to lecture number 6. This is SD classes and I am your physics sir, Mr. Sushan Dhali. Today we are going to learn the potential energy in an external field of a system. So we have three systems, single charge system, then 2-point charge system, and then last is your dipole. Let me start with the potential energy of a single charge system in an external field. So I have a xyz plane here. So here the xyz Cartesian coordinate, and these electric fields are parallel to the x-axis. Okay, and I have already taken a point P. Suppose this point P is denoted by the vector, the position vector r. Okay, now consider potential at P, B, VR. Okay, so at the point P the potential is your VR. And VR, why VR? Because the point P is denoted by the your position vector r. Okay, therefore we have written VR. Now suppose you want to carry a charge q from infinity to the point P, then what will be the work done? So work done to bring a charge from infinity to point P is equal to the potential at P into the charge that we are bringing from infinity to that point. Okay, so we know that this work done is equal to potential energy. So potential energy will be VR into Q. So we can say that energy potential energy of a single charge system in an external field is given by your Q into VR. So VR is the potential at that point where you are bringing the charge from infinity to the inside of the electric field. Okay, so this is all about the single charge system. Now let let us consider 2-point charges. Okay, let us consider at point A and point B. Okay, and the point A is denoted by the r1 vector, and point B is denoted by the position vector r2. Okay, now you want to bring a charge q1 charge first from infinity, so infinity to the point A. Okay, so suppose potential at A V VR1, and at B at point B VR2. Okay, so here the potential is VR1, and here at B point the potential is VR2. Okay, so to bring the charge Q1 from infinity to that point, will the work done will be, so the work done to bring Q1 charge to point A, what will be the charge work done? W1 will be your potential into charge. So potential is VR1 and the charge is Q1. So this is the work done, right? Similarly, suppose I am bringing another charge Q2 from infinity to the point B. Okay, so the work done to bring Q2 charge from infinity to B, let it denoted by W2, will be the potential at B, that is VR2, into the charge Q2. So this is the work done to bring the second charge from infinity to inside the electric field. Okay, now the question is, the first charge is already arrived before the second charge. Okay, so while bringing this charge, we have already q1 is also already present here, right? So now due to q1 we have an electric field here, not this external electric field, we have an extra electric field due to this q1, and the distance, this distance is r1 r12. Okay, so we know that due to this q1 we have a potential here vb, and the potential at b due to q1 charge is vb, that is equal to 1 by 4 pi epsilon naught q1 by r12. So now due to this charge, okay, we have another work done. Okay, so the work done to bring q2 to point b due to q1 charge is your w3, that is equal to w3 is equal to potential is your vb into your q2, so this will be equal to potential, that is vb into q2, that will be 1 by 4 pi epsilon naught q1 by r12 into q2, so this will be equal to 1 by 4 pi epsilon naught q1 q2 by r12. So this is the three kind of work that we have done to bring q1 and q2 charge inside an external field. So the total net potential, the net potential energy of this system, of the system, okay, will be your u will be sum of w1 plus w2 plus w3. So this will be equal to q1 v r1 vector plus q2 v r2 vector plus your 1 by 4 pi epsilon naught q1 q2 by r1. So we have three terms here. The first term is due to the electric field, and the second term is also due to the electric field, and the third term is the due to the electric field of the q1 charge that has been already arrived before the charge q2. Okay, so this is all about the potential energy of a system of two charge inside an external field. Next, we are going to learn potential energy of a dipole in an external field. So you can see here we have a dipole. Suppose the name of the dipole is AB, and here we have a minus q charge, and here we have a plus q charge. And we know that in an external field, the dipole will experience some torque, right? Suppose the torque faced by the, or experienced by the, you can write experienced by the dipole B, let it be tau pe sine theta. So what theta? Theta is the angle between your dipole moment and the electric field. So dipole moment is in the direction of AB, and the electric field is in the direction, in this direction. Okay, so the angle between them is theta. And we know that suppose due to the torque, right, due to the torque, it will rotate. Okay, it will rotate, the dipole will rotate. Suppose it is rotated by an angle d theta, small angle d theta. So this is the angular displacement here. Okay, so we have a force and we have a displacement, so there must be work done. So the work done to move the dipole by an angle d theta b dw. So suppose the small amount of work done is dw, right? So this will be your angular force into your angular displacement. So angular this force is tau and displacement is your d theta. Okay, so dw will be equal to d theta. In place of tau we can write, so angular force means your torque, okay, and angular displacement means your d theta, the angle by which it has moved. Okay, so we know that work done is in linear motion is the force into displacement, but here we have a rotational motion, so we have taken angular force into angular displacement. So we can write pe sine theta into d theta. Now suppose you want to find out the work done while a dipole has been moved from theta 1 to theta 2. Suppose the first angle is theta 1 and then it has been moved to another angle. Suppose the second angle is, so the second angle is here, suppose theta 2. Okay, theta 2 is the new position, so a dash b dash. So this is the a dash b dash is the new position and the new angle is theta 2 and the old angle is theta 1. And now the dipole has been moved from an angle theta 1 to theta 2. So what will be the work done, right? So to move an dipole, not an, a dipole by or from angle theta 1 to theta 2, we have, so integration dw from theta 1 to theta 2, this will be integration pe sine theta d theta theta 1 to theta 2. Okay, so it will be equal to dw is total work done from going from theta 1 to theta 2. Pe will be carried outside of the integration since they are constants. So theta 1 to theta 2, this will be sine theta d theta. Okay, so now sine theta d theta. So integration of sine theta d theta, integration of sine theta is equal to your minus cos theta. Integration of sine theta d theta is your minus cos theta. Okay, so here we can write w is equal to pe minus cos theta goes from theta 1 to theta 2. So this will be equal to w is equal to pe. So first of all theta 2 will come first, so this will be minus cos theta 2 minus minus cos theta 1. Okay, so this will be w is equal to pe minus cos theta 2 plus cos theta 1. Now let me show this. So at the end we have got w is equal to pe cos theta 2 minus cos theta, sorry, cos theta 1 minus cos theta 2. So I want to arrange this one, so I can write, if I take a minus common here, so this will be pe minus cos theta 2 minus cos theta 1. So theta 2 will come first, then theta 1 will go to later because I have taken a minus common here, right? So w will be minus pe cos theta 2 minus cos theta 1. So this is the, so u, therefore we can write u is equal to, so w, this work done is equal to potential energy, right? So u is equal to minus pe cos theta 2 minus cos theta 1. So this is the potential energy while moving the dipole from an angle theta 1 to theta 2. Okay, now let me take some special conditions. Special condition. Okay, so condition number 1 is, suppose we have started with an angle 0 degree. That means we have started the dipole while it is along the direction of the electric field. Okay, the dipole is lying along the direction of the electric field. The theta means 0 degree and theta to be theta. Then your u will be minus pe cos in place of theta 2 I will write theta, and here I will write cos 0 degree. So this will be equal to 1. So u will be minus pe cos theta minus 1. Okay, next is condition number 2. Suppose theta 1 is 90 degree. Okay, so what is theta 1 90 degrees? What is the position? This is the position. The second position is while the dipole is perpendicular to the direction of the electric field. Okay, so this is the initial position, and let theta 2 be any position theta. Okay, so this will be equal to, u will be equal to minus pe cos, in place of theta 2 I will write theta minus cos 90 degree. So this will be 0. So this is equal to your u is equal to minus pe cos theta, and magnitude pe cos theta can be written as in the form of vector, that is p dot product e. So these are the form of your potential energy when your dipole is started with the 90 degree angle. Okay, so this is the initial position of the dipole. This position is called your zero potential position. Okay, so in general the dipole is been firstly kept in this position, right? So while calculating the potential energy, we will consider that it is in the zero potential position. So therefore in general we only consider this formula to calculate the potential energy of this type of problems. Okay, not this formula. This formula is considered for solving problems related to your dipole inside an electric field. Okay, so this is the end of your LT6. I hope you have understand it, and this is also the last video of the series that we have started with explaining electrostatic potential and electrostatic potential energy. Well, after completing all the lecture, here I have a question for you. I hope you are able to solve it. Okay, the notes of this lecture and the answer of this question can be found in the description section. I hope to see you with a new video and with a new concept. Till then, enjoy learning. Bye bye.